video, we saw up to theorem 13.2, which talked about what is an integrable function and how can we figure out if a function is integrable. Okay, so now let us look at some results involving integrable functions. Theorem 13.3. If f is continuous on a closed interval, if f is continuous on a closed interval AB, then f is integrable on AB. Then f is integrable on A to B. On A to B. Proof. Well, the proof is relatively simple. F continuous on AB implies f is uniformly continuous. F is uniformly continuous, on AB, right? So take a partition P. Take partition P is equal to, let's say, T0, T1, dot, 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 up to Tn, such that, I forgot to say something. Well, let me say this first. Before we take a partition, therefore, there exists a delta greater than 0 such that for every x comma y in AB, such that absolute value of x minus y is smaller than delta, the absolute value sorry, let me just remove this such that for every x comma y in AB, x minus y smaller than delta implies f of x minus f of y is smaller than epsilon over 2 times b minus a. Okay. Well, great. I have chosen such a thing, and therefore, then take a partition P. Partition P is equal to T0, T1, up to Tn, such that the maximum distance between Ti and Ti minus 1 is always less than delta. Okay, delta. Well, in that case, therefore, well, mi minus small mi is going to be smaller than or equal, strictly smaller than epsilon over 2 times b minus a, right? Because the maximum value is going to be some f of x in the partition, the minimum value is going to be some f of x in the partition, and therefore all of it lies inside b minus a, which is also strictly smaller than epsilon over b minus a. Great. If you wanted to do it by, take f of x minus f of y, where f of y is the minimum and f of y is the maximum, then you might need the 2, but otherwise you don't need the 2. Well, therefore, u of f comma p minus L of f comma p, which is equal to, well, summation I is equal to 1 to n. If I take out the things common, I get this is mi minus small mi Ti minus Ti minus 1. Well, this is strictly smaller than epsilon over b minus a, each of these terms is smaller than epsilon minus times b minus a, summation I is equal to 1 to n ti minus 1, right? I'm saying that, oh, mi minus 1 is smaller than epsilon over b minus a. I'm pulling that out. Well, this is exactly equal to the epsilon over b minus a is a constant, and the summation I is equal to 1 to n ti minus 1. Well, it's basically the entire interval, right? So this is b minus a, which is equal to epsilon. Therefore, found a partition for which UFP minus LFP is smaller than epsilon. Therefore, it is integrable. Therefore, what was I saying? F is integrable on AB. F is integrable on A to B. Great! We have our first theorem where I know that a function is integrable without having to create a partition and do horrible things with it. Okay? Now, what are the properties of integrable functions? How do I figure out, can I do my standard things with them? I would like them to be preserved under addition or multiplication and all these things. And this is the first result. Let A smaller than C smaller than B. F integrable on AB. Integrable on A to B. I'm not saying it has to be continuous, just integrable. Well, it is integrable on AB if and only if F is integrable on A to C and C to B. Okay, and in that case, then integral from A to B of F is equal to integral from A to C of F plus integral from C to B of F. Okay, let's prove this. Proof. So there are two parts, right? I want to show first in the forward direction and second in the backwards direction. So let's do this direction first. Suppose F is integrable on AB. Suppose F integrable on AB. Then there exists a partition P such that, well, let me just write. Then there exists P is equal to T0, T1, Tn of such that U of F comma P minus L of F comma P is smaller than epsilon, right? Oops, I forgot to mention this. Then, given epsilon greater than 0, there exists such a partition. However, so given epsilon greater than 0, I can find such a partition. Well, we can assume Tj is equal to C for some j. Otherwise, add it as an extra. Add it as an extra element. right? I can just add another number in there, C, wherever it actually fits, and that's a new partition which again satisfies this property. If I'm already satisfying this property, we have seen that a further smaller partition would satisfy this property. Okay, great. Then consider T1 is equal to T0 dot 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 C or Tj, and P2 is equal to Tj dot 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 Tn. Then, well, the lower sum LF comma P is equal to LF comma P1 plus LF comma P2, and similarly the upper sum LF comma P is equal to UF comma P1 plus UF comma P2, right? And therefore UF comma P minus LF comma P is equal to, I can write this as UF comma P1 minus LF comma P1 plus UF comma P2 minus LF comma P2, and well, this is exactly equal, and that is strictly smaller than epsilon. And since both of these are positive, therefore both of these also have to be smaller than epsilon. Therefore each of these is smaller than epsilon. Therefore this is smaller than epsilon, and this is smaller than epsilon, right? I can't say that each of them is smaller than epsilon over 2. I don't know, one of them might be epsilon over 2 bigger than epsilon over 2, and the other one might be epsilon over 700 or something, but their total is smaller than epsilon, so each one of them is smaller than epsilon since these are positive, right? Let me just write, oops, since both terms are positive, both terms are actually non-negative. Okay, so since both terms are non-negative, this is going to happen. Okay, also so therefore both of these, therefore f is integrable, integrable on AC and CB. Great. And also LF comma P1 is smaller than or equal to integral A to C of f smaller than or equal to U f comma P1, and LF comma P2 smaller than or equal to AC to B f smaller than or equal to U f comma P2, and therefore LF comma P is smaller than or equal to A to C f plus C to B f, which is smaller than or equal to U f comma P2. Whoops, not P2, just P, right? Because I'm just adding these two. Let me draw a very big plus here. So I'm adding these two, therefore I get this, and that proves that therefore A to C f plus integral C to B f is equal to integral A to B of f, because this middle term it should be equal to f, right? The thing that lies between the two in the limiting case is exactly a to b of f. Well, that shows the forward direction. For backward direction, it's incredibly easy. There exists P1 or partition P1 and P2, partitions of A to C and C to B respectively, such that, well, u of f comma p1 minus u of f comma p2 is smaller than epsilon over 2, and such that, okay, where's this first? I keep forgetting this part. This direction, given epsilon greater than 0, there exist partitions such that epsilon greater than 0, such that L of f comma p1 is smaller than epsilon over 2 rather than epsilon, and u of f comma p2 minus L of f comma p2 is also smaller than epsilon over 2. Then P is equal to P1 union P2 is a partition of A to B, which satisfying L of u of I'll just write it. LF comma P is equal to LF comma P1 plus LF comma P2 u of f comma P is equal to u of f comma P1 plus u of f comma P2, and therefore u of f comma P minus L of f comma P is equal to, well, the sum of these two, or let me just say subtraction of these two. So u f comma P1 minus L f comma P1 plus u f comma P2 minus L f comma P2, which is smaller than or equal smaller than epsilon over 2 plus epsilon over 2, which is exactly equal to epsilon, right? And therefore this is the exact partition that we wished for. Therefore f integrable on A to B, and again same argument as before, it tells you same argument as before, it gives us integral A to B of f is equal to integral A to C of f plus integral C to B of f. Okay, so that's my theorem 4. Note, integral A to A of f is always 0, right? Because, well, there's only one partition, which is just T0. I don't have any other things. The max is value f of a. The min is f of a. If I do When I try to multiply by the length of the interval, that part is 0 though. So that gives you 0. Also, integral a to b f is equal to integral negative integral b to a of f if a is smaller than b. Well, actually, the second part doesn't matter. Even if a is greater than b, it doesn't matter. Okay? Whichever way you define it, you're going to get this, because you can just use the same partition in reverse, and every single term in your sum then suddenly becomes negative, right? So you can pull out a negative from all of these. So theorem 5, yeah, I'm inconsistent about theorem and THRM. There are two parts. I'm going to club theorem 5 and 6 from the book in one. If f comma g are integrable on AB, are integrable on A to B, then first A, f plus g is integrable, and integral a to b of f plus g is equal to integral a to b of f plus integral a to b of g. And b, I shouldn't have called these a and b, I should have called these 1 and 2. I'm already using the letters a and b, 1 and 2. For a constant, for any constant c, for any constant c, cf is integrable, c times f is integrable on a to b, and integral a to b of c times f is equal to c times integral a to b of f. Proof. Okay, I am not going to prove part B. Part B is really easy. Hint, find out how the minima and maxima, so how the infimums and supremums in each small interval are. How are they related to minimums and maximums of f? Okay, so that one's really easy. We'll only do part 1. So let P be any partition. Let P is equal to T1, T0, T1, Tn, partition of AB, partition of AB, and let Mi is equal to, as usual, my infimums on this time f plus g of x, such that, well, x is in ti, well, whatever, ti minus 1 smaller than or equal to x smaller than ti, mi prime is equal to infimum of f of x on the same interval, okay, and mi double prime is again infimum of g of x on the same interval, okay, which is the closed interval ti minus 1 to ti. Okay, similarly define mi prime and mi double prime. Okay, so now note, it is not true, it is not true that small mi is equal to mi prime plus mi double prime. Okay, this is not true. This is very important. However, what is true? However, mi is actually greater than or equal to mi prime plus mi double prime. Okay, it is always going to be greater than this. Similarly, big Mi is smaller than or equal to capital Mi prime plus capital Mi double prime. Okay, well, what does that mean? Therefore, L of f comma p plus L of g comma p is smaller than or equal to L of f plus g comma p, and u of f plus p, f comma p plus u of g comma p is greater than or equal to u of f plus g comma p. Okay, great. And therefore I get therefore L of f comma p plus L of g comma p is smaller than or equal to L of f comma p, f plus g comma p, f plus g comma p, which is further smaller than u of f plus g comma p, which is further smaller than u of f comma p plus u of g comma p. What that means is, if I take partition if since f and g are since f comma g are integrable on a to b, for given epsilon greater than 0, there exists p1 comma p2 such that u of f comma p1 minus L of f comma p1 is smaller than epsilon over 2, and u of g comma p2 minus L of g comma p2 is smaller than epsilon over 2. Therefore, what did I want? Yes. Therefore, P is equal to P1 union P2 satisfies u of f comma p plus u of g comma p minus L of f comma p plus L of g comma p smaller than epsilon. Okay, great. This is the maximum possible value of this is greater than or equal to u of f plus g comma p. This is smaller than or equal to L of f plus g comma p, and therefore that means u of f plus g comma p minus L of f plus g comma p is smaller than epsilon, given any epsilon. Therefore, f plus g is integrable on a to b. Integrable on a to b. Okay. Moreover, because L of f plus g, L of f comma p plus L of g comma p is smaller than or equal to L of f plus g comma p. Well, because my function is integrable, I know that this is smaller than or equal to integral a to b of f plus g, right? And this is smaller than or equal to what do you call u of f plus g comma p, which is again smaller than or equal to u of f comma p plus u of g comma p, u of g comma p. I get that, hey, this lies in between these two, where the limit is in the limit the infimum matches up, and so does, and also by addition, L of f comma p plus L of g comma p smaller than integral a to b of f plus integral a to b of g is smaller than or equal to u of f comma p plus u of g comma p, right? Because integral of f lies between LF and UF. Integral g lies between LG and UG, right? And so I get that, hey, if I make these, if I'm looking at the infinitesimal limit, I get, if I subtract both of these sides, I can make this smaller than or equal to epsilon. Okay, subtracting top and bottom, I can get, therefore, integral a to b f plus g is equal to integral a to b f plus integral a to b g. Since basically I can make this difference ab, since b minus a can be made smaller than or equal to, can be made smaller than or equal to epsilon for every epsilon greater than 0. That means this has to be exactly equal. In the infimum case, in the supremum of a has to be infimum of b. Both of these are exactly that. Therefore, we get that they have to be equal. Okay, that's my theorem 5 and 6 combined. Exercise. Find integral a to b, integral c to d, f of x, g of y, dx, dy. Well, actually, you know what? I don't think I want to do this one. Because we haven't yet introduced the notation. So let's instead do this one. First, f defined on dE, f defined on 0 to b, f of x is equal to x, show that f is integrable. Well, actually, never mind. We have already shown the stronger result. So forget about these two examples. You can just, yeah, let me give you better problems. Well, sure. Exercise f defined on a to b on, let's say, 2 to 7 as f of x is equal to x squared x between 2 to 4 and is equal to x cubed. Well, I don't want to go to x cubed. So 2x plus 8 and x between 4 to 7. Show f is integrable. Okay, and maybe if you want, find its value later on. Easiest thing, check if it is continuous on the entire thing. Answer: f continuous on 2 to 7. Therefore, as let me correct this. This was supposed to be 2 to 4 as x squared as 4 squared as limit x approaches 4 minus of f of x is equal to f of 4 is equal to limit x approaches 4 plus of f of x. Therefore, f is integrable on 2 to 7. Ta-da! Simple enough. Okay, so then let us look at some more theorems and finish the chapter. THRM, theorem 7, whatever, theorem 6, which, whatever, I'll just call it theorem 6. If f is integrable on a to b, f integrable on a to b, and small m is smaller than or equal to f of x, smaller than or equal to capital M for every x in a to b, then m times b minus a is smaller than or equal to integral a to b f is smaller than or equal to capital M times b minus a. Okay, so we have now some estimate of the value of a and b without having to calculate the complete integral. It is clear that given any partition, m times b minus a is smaller than or equal to L of f comma p for every p. Similarly, m of m times b minus a is greater than or equal to u of f comma p. Well, therefore, mb minus a smaller than or equal to l f comma p smaller than or equal to a to b f smaller than or equal to u f comma p smaller than or equal to m times b minus a. Ta-da! And that is done. Okay. Nice and easy result. Now, let us do one slightly complicated result, which will set us up for the next chapter, which will be the fundamental theorem of calculus, and that is theorem 7. Theorem 7, which is theorem 13.8 actually. So this is the 8th theorem in book because I combined 6 and 5 together. If f is integrable on a to b, and capital F of x defined on a to b by capital F of x is equal to integral a to x of f, then the best I am saying right now is f is continuous on a to b. We'll later on see what is special about this function capital F. But right now, we're only going to say it is continuous. Okay, so how do we prove this? Suppose C belongs to A to B. Suppose C is some number in A to B. Okay, and since f is integrable on a to b, by definition it is bounded. F integrable on a to b implies let me just say this. F integrable on a to b implies f bounded, and on ab, and this is by definition. Okay, by definition, we defined our function to be integrable only if it is bounded. Therefore, there exists m such that f of x absolute value is smaller than m, smaller than or equal to maybe, for every x belongs to a to b. Great. I don't know if it's continuous or not. Well, I know that for any h greater than 0, if h greater than 0, even if h is not greater than 0, f of c plus h minus f of c, since f of x is defined the way it is, this is integral a to c plus h f minus integral a to c of f, and that is going to be integral c to c plus h of f, right? And that is smaller than, and m minus m is smaller than or equal to, and as minus m is smaller than or equal to f of x is smaller than or equal to m for every x, I get that minus m times h is smaller than or equal to c to c plus h f smaller than or equal to capital M times h, by the previous, exactly the previous result. Right? Well, but what is this? This by definition is therefore, minus m times h is smaller than or equal to f of c plus h minus f of c smaller than or equal to capital M times h. Right? Well, what do I get? Similarly, by reversing, why am I writing commas? Similarly, f of c plus h minus f of c is equal to minus c plus h to c of f, right? And therefore I get that mh is smaller than or equal to c plus h to c f smaller than or equal to negative mh by the exact same argument, right? Which therefore implies, well, mh is smaller than or equal to f of c plus h minus f of c is smaller than or equal to negative mh. Okay? Because this interval has the length negative h. Okay? On c plus h comma c. So you can technically think that OH is a negative number. So that is why you get this. What this means is, therefore, f of c plus h minus f of c is smaller than or equal to capital M times h. Absolute value of this is smaller than absolute m times absolute value of h. And therefore, taking epsilon, given epsilon greater than 0, I can get f of c plus h minus f of c is smaller than epsilon by taking absolute value of h is strictly smaller than epsilon over m. And therefore, this means that therefore, limit h goes to 0, f of c plus h is equal to f of c, and therefore the function is continuous as it. F is continuous at c. Okay, and that proves our big theorem. Okay. What am I doing? Right. C. Since this is true for every c, it is integrable on the entire interval a to b. Okay. I am going to stop this video here. This technically finishes chapter 13. I might do some examples of it next week probably. I'll finish chapter 14 also, and then do some examples of both of them together before your final exam. Okay, so that you have some examples to look at.